Okay, so I'm going to talk about some joint work with Borman and Varolgunes, and a little bit about the history of the work is that Borman and I announced a result quite a while ago, and then it didn't get written up, and then recently Varolgunes joined the project, whipped it into shape in a slightly different direction, kind of improved it, and now it's finished. So none of the blame for the long delay from the announcement belongs to him, and a lot of the credit for finally getting it over the line does go to him. Right, big screen. Okay, so I'm going to spend a bit of time introducing the basic players in this work, and focusing on how it relates to mirror symmetry. So one is quantum cohomology. So we're going to have a compact monotone symplectic manifold, where by monotone I mean the class of the symplectic form in H2 is equal to the first Chern class. And we define the quantum cohomology of M with coefficients in some Novikov type field K, formal power series in a Novikov variable Q. And the quantum cohomology is just by definition the cohomology of M with coefficients in this field. And this is equipped with the quantum cut product, which where the coefficient of the quantum cut product of alpha with beta paired with gamma is the number of holomorphic curves U with constraints on cycles Poincare dual to alpha, beta, and gamma, weighted by Q to the symplectic area of this curve. So, for example, quantum cohomology of projective space is a deformation of the usual cohomology. So we get this single generator H and single relation H to the n plus 1 equals Q to the n plus 1. And when we set Q equals 0, we get back classical cohomology. So symplectic manifolds of this type are related by mirror symmetry with a Landau-Ginzburg model, which is by definition a K variety Y equipped with a regular function W called the potential. And mirror symmetry predicts that quantum cohomology of M should be isomorphic to the algebra of functions on the derived singular locus of W, which, when the singular locus is isolated, is just the same thing as the algebra of functions on the singular locus. And when your variety Y is affine, this is just some Jacobian ring. So, for example, the mirror to CPN is the algebraic torus over K, together with the superpotential I've written here. This one here. And mirror symmetry predicts that quantum cohomology of CPN is isomorphic as an algebra with the Jacobian algebra of this function W. It's the quotient of the coordinate ring by the partial differentials of the potential. And I've written down here what the isomorphism between them is. So it's not hard to check. Of course, mirror symmetry there are more refined predictions which have more content, but I just want to say the most basic prediction of mirror symmetry, and you'll see how that emerges in our work, and any more refined version, like Frobenius manifolds and all the rest of it, you can imagine can be obtained by, can play a role in our work by refining it in the appropriate ways. But we'll just focus on this simplest version of the mirror prediction between a compact monotone symplectic manifold and the mirror Landau-Ginzburg model. So in our work, we're going to think of quantum cohomology rather than in the way I've defined it just now. We're going to think of it as the Hamiltonian Floer homology of M. We'll have a brief review of that. So this says that we take a family of smooth functions on M, parameterized by the circle, an S1 family of smooth functions. An orbit of this family of smooth functions is a loop in M, so that the derivative at time t is the Hamiltonian vector field associated to the function ht. And a Floer trajectory connecting two orbits is a solution of this partial differential equation, Floer's equation. And this allows us to define, that Floer proved that you can define a chain complex where the generators are orbits of the Hamiltonian, and the differential is defined by the coefficient of gamma plus in the differential applied to gamma minus is the count of Floer trajectories connecting gamma minus with gamma plus, weighted again by some power of q, being a little imprecise here, but it's related to the symplectic area. And the Hamiltonian Floer homology of M is the cohomology of this chain complex, of this cochain complex. And Floer proved that this Hamiltonian Floer homology is independent of H and isomorphic to the quantum cohomology of M. So the slogan is that it localizes at the constant loops. It's some kind of, you can view it as more homology on the loop space for some action function along the loop space, and it localizes at the space of constant loops, which is a copy of M. And this isomorphism, by a result of Punikin, Salomon, and Schwarz, intertwines the pair of Pence product on Floer homology, which counts pseudo-holomorphic pairs of Pence like this, and that gets intertwined with the quantum cut product, which I defined on the previous slide. So that's how we're going to think about quantum cohomology for the purposes of the talk. We're also going, the other main player in our result is symplectic cohomology, which is a version of Hamiltonian Floer homology for non-compact symplectic manifolds. So in particular, we'll talk about Liouville domains, which are symplectic manifolds equipped with a primitive theta for the symplectic form, such that when you define the Liouville vector field Z, which is defined by this equation here, then it points outwards at the boundary or at infinity. So there's a nice sort of structure theorem for these Liouville domains. There's a part that looks like the product, a symplectization of the contact boundary of your Liouville domain, where it's got sort of the contact manifold in this direction, and the symplectization direction is going along the flow lines of Z. And when you remove that symplectization of the contact boundary part, you're left with some isotropic cell complex, I guess you can say, some singular set called the skeleton. which is the limit set of this, the negative of this Liouville vector field. And you can define a function rho, which is defined so that, rho equals 1 along your contact boundary, and z of rho equals rho. And this defines some real function which goes to 0 on the skeleton. And we define the symplectic cochain complex to be the Floer homology of X equipped with some Hamiltonian that goes to infinity sufficiently fast near the boundary. So it looks like it's some function of this rho, where the function kind of goes to infinity as rho goes to infinity. So this symplectic cohomology also fits into mirror symmetry. So a typical mirror to a Liouville domain might be a K variety. And the symplectic cohomology might then be isomorphic to the tangential, what's called tangential cohomology, which is what I've written here, the sheaf cohomology of the polyvector fields on Y. So as an example of that, you can see that C star is mirror to C star. The symplectic cohomology has generators coming from constant loops, which you can call 1 and Z del del Z. It has generators coming from loops going once around at one end, call that Z inverse and del del Z. Once around at the other end, call them Z and Z squared del del Z. Loops going twice around at both ends. And you end up labeling all of these by the generators of the tangential cohomology of C star, which I've written over here. And this isomorphism respects various natural algebraic structures that exist on both sides. Okay, so now I'm going to introduce the geometric setup where we work and prove our results. So we start with a compact monotone symplectic manifold, as I introduced before. And we introduce a new object, which is a simple crossing symplectic divisor. So this means a union of real codimension 2 symplectic submanifolds Di, which intersect transversely, and such that together with some data that the induced orientations on or co-orientations on all of the strata agree with there's some compatibility data that I won't go into on the how they're allowed to intersect. They sort of intersect positively in some sense. And we choose additional data called weights, which is these positive rational numbers lambda I, so that the class of the symplectic form, which we remember is equal to C1, should be equal to the sum of lambda I times the Poincare duals of these divisors, Di. And we define X to be the complement of this divisor in M. So this allows us to naturally define a structure of Liouville manifold on X. Well, sorry, I shouldn't say naturally. One can define there exists a choice of primitive theta for the symplectic form omega. So I should have said omega restricted to X, so that X becomes a Liouville manifold. And the role that the lambda I play in this choice is that the class in relative cohomology given by omega together with theta is given by this combination of Poincare duals of the divisors. So the most natural source of examples comes from algebraic geometry. We can take M to be a smooth Fano variety, omega to be a Kähler form, the curvature of some Hermitian metric on a power of the canonical bundle. We can take the divisor to be a simple normal crossings divisor where the section defining it is a section of this power of the canonical bundle, which vanishes toward a roughly lambda I along the divisor di. Then x is m minus d, and we can say that sort of this combination of the divisors di is anti-canonical. So that's our setup. And the conjecture is that under appropriate hypotheses, the Floer cohomology of M, which we recall computes quantum cohomology, the Floer cochain complex of M, which computes quantum cohomology, should be a deformation of the symplectic cochain complex of X. And there should be a resulting spectral sequence from this this deformed complex equipped with the Q-adic filtration should give us a spectral sequence associated to the filtered complex, where the E1 page is given by the symplectic cohomology and it converges to the quantum cohomology. Symplectic cohomology of this affine variety converging to the quantum cohomology of the compact variety. But I mean, this idea was around, but it was known that, you know, some hypotheses were needed because of the very simple counterexample to the conjecture when M is projective space and D is a hyperplane, then X, the complement of D, is just affine space, which is well known to have vanishing symplectic cohomology. And you certainly can't have a spectral sequence from 0 converging to the quantum cohomology of CPN, which is certainly not 0. But yeah, our aim is to come up with appropriate hypotheses under which this is true. And the mirror symmetry motivation working in the log Calabi-Yau case, because it's simplest to state there, goes like this. So if our affine variety X is mirror to some K variety Y, then we expect that our compact variety N is going to be mirror to Y with coefficients changed to from little k to big K. So recall, so this was big K is power series is Laurent series in Q. Little k is the coefficients of the Laurent series. So this one is like little k. This one's big K. So the conjecture is that the compactification is Y with excitation coefficients changed to big K, equipped with some potential W. And symplectic cohomology of X is expected to be mirrored to, well, what I wrote was equivalent to hypercohomology of a complex of sheaves with trivial differentials, where we've got O of Y, Ty, this is going to be wedge 2 Ty, etc. And then there's a hypercohomology spectral sequence. So there are two hypercohomology spectral sequences, depending on which which way you look at the bicomplex, but this is called hypercohomology spectral sequence 2, where the hypercohomology of this thing with zero differential converges to hypercohomology of the same complex, but where you've turned on a new differential, which is contraction with dw. And the hypercohomology of this is, by definition, the algebra of functions on the derived singular locus of W. In particular, when W has isolated singularities, it's just algebra of functions on the singular locus. And that's precisely what we expect to be mirror to quantum cohomology. And our conjecture says that, so the conjecture here is supposed to fit in with this commutative diagram. All right, so let me now state our results. So the first theorem says that there exists a filtered chain complex, which we'll call SC tilde, whose associated graded is quasi-isomorphic to the symplectic cochain complex, with coefficients changed to this power series ring, Laurent series field. And if we don't take the associated graded, then it's quasi-isomorphic to the Hamiltonian Fleur cochain complex of M. And there was this, we had to change the coefficients a little bit. Don't worry too much about it. It's just, we take a generator Q to the A, where A is a generator of the span of these weights, lambda I. Okay, so you might look at theorem B and say, I mean, theorem B already says well, I shouldn't say implies. I mean, but from theorem B, we get a spectral sequence with E1 page SH symplectic cohomology from part A. And the filtered complex we're constructing the spectral sequence from has cohomology, quantum cohomology of M. So you might think that we're done. The tricky bit is about the convergence of the spectral sequence. And for that, we need a hypothesis, which is we require that these weights, lambda I, should be less than or equal to 1 for all I. So in the algebraic geometry setting, this has an interpretation in terms of the log Kodaira dimension of the pair MD, or the affine variety X. So this hypothesis, well, X could be thought of as log general type if lambda I is strictly less than 1 for all I. Strictly speaking, that's only true if all the components of D are individually ample. But then this does coincide with the notion of X being log Calabi-Yau when lambda I equals 1 for all I. And if lambda I were all bigger than 1, then this would be called log Fano. So roughly speaking, the applicability of our results is when M should be Fano, or Calabi-Yau, so it should have Kodaira dimension negative or non-positive, and X, the affine variety, should have Kodaira dimension non-negative, roughly speaking. And what we get under this hypothesis is that this spectral sequence that we conjectured should exist under some hypotheses does exist, does converge to the quantum cohomology of M. And so we work in this case where M is Fano, but by work of MacLean and Yuhan Sun, an analogous result has been proved in the case that M is Calabi-Yau. Okay, and then using machinery developed by Varolgunes, we're able to give some nice applications of the ideas that come up in the proof of these theorems B and C to symplectic topology. Namely, under hypothesis A, we can show that the skeleton of the affine variety X is what's called SH full, which I won't say exactly what it means, but it implies that S is non-displaceable in M. I should have specified. And intersects any Floer theoretically non-trivial Lagrangian, and analogous results were proved by Tonkonog and Varolgunes in the case that M is Calabi-Yau. But I should say that in both of these cases, in MacLean and Sun's work and Tonkonog Varolgunes' work, this hypothesis A is not necessary. So that's something specific to this Fano case. Oh, and also I should say that in this theorem D, that there's a refinement. If you don't have hypothesis A, then we also have some specific neighborhood of the skeleton, which is SH full. So somehow under hypothesis A, this skeleton kind of sees all of the Floer theory of M. And if you don't have hypothesis A, then you need to take some specific size of neighborhood of S, and then that somehow sees all of the interesting Floer theory of M. Okay, so here are two examples aimed at this understanding this theorem D a bit better. So if we take M to be a two-sphere, our divisor D will be a collection of points, and the weights lambda I will have to add up to the Euler characteristic of the two-sphere, which is 2, which is also going to be the area by our monotonicity assumption. Then this skeleton S is going to be some kind of graph inside the two-sphere, which splits it into regions, each one containing one of these points, and the region containing Pi is going to have area lambda I. And this skeleton, you can see, will be displaceable if and only if all of these lambda I are less than or equal to 1, which is precisely what hypothesis A says. Because if you had one that was area bigger than 1, that would say you had more than half of the area in that thing, and you could sort of rotate the skeleton inside that bit that has more than half the area. So you sort of rotate the whole skeleton to put it inside that region. Another example is when M is a Fano-toric variety. So it's known that there's sort of one fiber of the moment map is the one where all the interesting Floer theory is. And it turns out that the sort of hypothesis A can only be satisfied if all of the weights are equal to 1. So we're in this log Calabi-Yau setting. And if any of the weights are not equal, and in that case, the skeleton is going to be precisely this most interesting monotone torus fiber. And if we change any of the weights so that they're not 1, then hypothesis A will not be verified, and the skeleton will be one of the non-interesting torus fibers. So this is about the sharpness of this theorem D. So let me tell you a bit about how the proof goes. So the idea is to look at the Hamiltonian Floer cochain complexes for some family of functions hi, where hi, roughly speaking, is getting bigger and bigger along the divisor. So this means that when you restrict hi to the affine variety x, then it's the kind of family of functions that you can use to compute the symplectic cochain complex of x. So Floer cohomology of M doesn't depend on the Hamiltonian. So all of these cochain complexes, Floer cochain complexes of the function of the Hamiltonians hi, are quasi-isomorphic. So if we take a direct limit, we're just going to get Floer cohomology of M. And the idea is that each of these complexes can be split into a piece that corresponds to orbits in X and a piece that corresponds to orbits on the divisor D. And then we play some games with gradings that show that these orbits on the divisor D can be cancelled out. Like you can find some quasi-isomorphic subcomplex which doesn't include any of those orbits. And so you're left just with the orbits in X, which precisely compute the symplectic cochain complex of X, except that the differential counts Floer trajectories in M rather than Floer trajectories in X. So you expand out this Floer differential in powers of the Novikov variable Q, where the coefficient of Q to the J counts Floer trajectories which pass J times through the divisor. So they'll always, whenever a Floer trajectory hits the divisor, it hits it with non-negative, with positive multiplicity by positivity of intersection. So in particular, the lowest order part of this differential just counts trajectories which don't hit the divisor at all, and in particular stay inside X. So the del zero is just the differential on the symplectic cochain complex. And to get this differential on the whole thing, we have some deformation. We add some higher order terms in Q. And this is how we get our theorem B, which, recall, just said that we had some chain complex, which roughly speaking computed symplectic cohomology, it's associated graded, computed symplectic cohomology, but the whole thing computed Floer cohomology of M. So the reason we have this kind of SC tilde is about this game about throwing out orbits on D. That's sort of why it's not exactly, why we can't just use symplectic cochain complex. We need to do some game with gradings and filtrations to get rid of these orbits on the divisor D. And then for theorem C, the bit about convergence of the spectral sequence, we need to show that the q-adic filtration is bounded below. And the idea there is to compute gradings of the generators of this symplectic cochain complex. And it turns out that the grading of a generator going k times around the divisor di is 2k times 1 minus lambda I. So hypothesis A is basically saying that all of these generators are in non-negative degree, and this is what gives us the filtration is bounded below. Okay. Sorry, maybe I should ask if there are any questions. Sort of going at breakneck pace, and I might finish early.
Seems not. If anyone wants to, I have the microphone here.
Do you hear me if I speak like this?
I can't hear. Did someone speak?
I'm coming with a microphone.
Thank you so much. Hi. So I was just wondering, with your result, can you explain what happens if you start with a, I don't know, log Labial, and then you kind of smooth the divisor? Like, do you understand how symplectic cohomology changes? I mean, perhaps in an example.
Yeah, I mean, it's kind of a, I mean, this is a different, I mean, I can say that the answer is complicated because already if we talk about the example of CP2, so if you've got the example of M as CP2, D is the toric boundary. So in this case, this is quite this is quite simple. This symplectic cohomology of X with the toric boundary is, I mean, this is symplectic cohomology of C star squared, which is polyvector field cohomology of the mirror C star squared. Now, so if you smooth D to a line union a conic, then the mirror changes. So this is mirror to so it's actually self mirror. And so, I mean, this is the focus singularity, and it's mirror to itself. And you know so this is a cluster variety, but it's got two cluster charts, and you know so somehow it's all I can say is that there's it's complicated in the simplest possible example. I think, sorry, people's names don't need math bold font. I heard a talk by Hua Nguyen on a related idea about how symplectic cohomology changes under this procedure. There may be updates on this more recently, but yeah, I mean, typically if you smooth the divisor, I mean, the mirror is going to change, like in this case. I mean, we get a different mirror I mean, X has a different mirror, and you get another, sorry. And it's, I mean, putting a different divisor inside M is going to lead to a different mirror to M. Like this toric boundary divisor gives you the mirror C star squared equipped with the well-known potential. This line union conic divisor gives you the mirror is this Y equipped with a different potential. It's a different affine variety equipped with a potential. So our theorem applies to both things, the divisor smoothed and unsmoothed, but yeah, I can't say anything about how this procedure changes symplectic cohomology, or at least that's not the subject of this talk. Yeah, sorry. Any other questions?
Apparently not. You can continue.
No? Okay. So I'll carry on to the bit of the talk that is more speculative, which is so actually the original result which Borman and I announced was a refinement of theorems B and C, which said that the deformation from symplectic cochain complex of X to the Fleur cohomology of M should be controlled by a Mora-Cartan element for the natural L infinity structure on symplectic cochains on X. So this is a more precise version of the statement, because I mean we have Mora-Cartan deformation theory. We can classify Mora-Cartan elements for L infinity structures, so there's somehow a space of deformations that arise by this procedure, whereas in the version of the statement that I gave, yeah, I mean, you can't classify deformations of a chain complex, or it's not a natural deformation theory problem. But for now, this remains a conjecture. Well, I think we have a good idea about how to do it. So in the log Calabi-Yau case, this refined version of the statement would have the following consequence for mirror symmetry. So suppose we had mirror symmetry for the affine variety X being mirror to polyvector field cohomology of Y. Then the conclusion of the theorem is that if we deform symplectic cohomology by this Mora-Cartan element beta, so if we deform symplectic cohomology by this Mora-Cartan element beta M, then we get by the conjecture, we get this quantum cohomology of M. And in particular, on this side, we deform, the corresponding thing to do is to deform by the Mora-Cartan element corresponding to beta M. And it turns out that for degree reasons, the only Morikatan elements can be functions on Y. So in particular, given this mirror symmetry for the affine variety X, it says that the compactification from X to M determines a function W on the mirror such that quantum cohomology of the compactification M is isomorphic to functions on the derived singular locus of W. So this refined version of the conjecture would say, once you've proven mirror symmetry for the complement of an anti-canonical divisor in a Fano variety, you get for free mirror symmetry for the Fano variety, or some version of it. I mean, you can also talk about versions of this that that work for homological mirror symmetry as well. So it somehow gives you an automatic upgrade of your mirror symmetry statement from the affine part to the compactification. Okay. And the last thing I want to talk about is a generalization, a conjectural generalization of our theorems B and C, or theorem C, I should say, which was suggested to us independently by Pomigliano and Seidel. And so the question there is, what do we, I mean, so if we go back to the statement of theorem B, I said down here, from theorem, so theorem B gives us this filtered complex. And in particular, it gives us a spectral sequence whose E1 page is the symplectic cohomology. And the question here is, okay, well, under hypothesis A, this converges to quantum cohomology of M. But if we don't have hypothesis A, might this spectral sequence nevertheless converge to something interesting? And the conjecture, for which there's some evidence, is that it does. We expect that it should converge to a sub-algebra of the quantum cohomology of M, which I'll call QHM crit, which is the intersection over all I such that lambda I violates hypothesis A, of the zero generalized eigenspace for quantum cut product with Poincare dual of DI. And maybe the most, I mean, there's a sort of outline of why this is a reasonable guess, but there's also an explicit verification of this conjecture, which in fact goes back to 2010 by Eliashberg and Polterovich. So, I mean, this serves as part of the motivation for the conjecture in the first place. So they considered the case that M is CP1 cross CP1, D is a 1-1 smooth hypersurface in M, and S is the skeleton of M minus D, which turns out to be smooth. It's a Lagrangian two-sphere. And Eliashberg and Polterovich constructed a spectral sequence from the symplectic cohomology of the two-sphere to this QH of M crit, which is just the zero generalized eigenspace of quantum cut product with omega in this case. And it's interesting to contrast this with results of Ritter and Venkatesh. So if you take say a Fano variety B equipped with a line bundle whose first Chern class is a negative multiple of the first Chern class of B, that's what I mean by a negative line bundle. Then what Ritter shows is that the symplectic cohomology of X is kind of opposite to what we get. He gets the quantum cohomology of B mod the zero generalized eigenspace. And Venkatesh does some quantitative version of this, sort of showing that, roughly speaking, as you take kind of bigger and bigger neighborhoods of the zero section of this line bundle, you kind of see more and more of the eigenspaces, the generalized eigenspaces of quantum product with omega, until you get sort of the whole total space of the line bundle, and you somehow get all of the generalized eigenspaces except for the 0th one. So there's kind of an intriguing parallel between this this conjecture and their results, or sort of complementarity, that we don't know exactly how to put them together. Okay, I think I'll stop there. Thank you.
Thanks, Nick, for the nice talk. Are there any questions?
Hi, thank you very much. So I had a question about what you said just at the very end about this symplectic cohomology of a negative line bundle. And to simplify, let's just think about like P2, P2 and O minus 3.
Yeah.
And so in enumerative geometry, in terms of like log invariance and local invariance, there's like really very strong connection between O minus 3 and P2, and like P2 relative to a smooth anticanonical divisor. So I was just wondering whether this like relationship in terms of log and local Gromov invariance extends to something at the level of symplectic cohomology.
Yeah, I don't know the answer. Sorry. I mean, I guess I guess you would hope to be able to compute the differential on this symplectic cohomology of say a divisor complement in terms of something like these relative or log Gromov-Witten invariants, and I think this is sort of in some sense this is what Ritter kind of does. He computes the differential sort of using No, I'm sorry. I can't remember. I think he, I think it might be possible to interpret his computation like of the differential in terms of something like log Gromov-Witten invariance in some simple case, but I can't see the precise. I can't tell you the precise connection.
Thank you very much for this. But is there some like understanding from mirror symmetry how the two would be related? Maybe just some general understanding. Thank you so much.
Sorry, I think I just don't know enough about log Gromov-Witten invariance. I mean, somehow, I mean, I kind of think about, I think about the invariants that play a role in mirror symmetry as sort of being defined by pseudo-holomorphic, curve equations and log Gromov-Witten invariants, and being, I think about them as a way of a better way of computing the things that are defined using pseudo-holomorphic curve equations, and I don't know how to think about their interpretation independently, but that's probably just my own shortcoming.
Yeah. Thank you so much for this. I guess my second question was maybe just on the B model side. Is there like a relationship which is as simple as like twist by a divisor versus remove a divisor, but maybe not. But like how the mirrors are related, if they are in any way.
So, sorry, twist by a divisor versus remove.
So sorry, if you look at O-3,
yeah,
right, and if you versus P2 relative to a smooth elliptic curve. Anyways, if there's this enumerative relationship, I guess my question was: is there some like B model relationship, or maybe not at all? Maybe the answer is just not at all. Maybe it's not the forum to discuss this.
Probably not, but that's my fault.
Thank you very much.
Sure.
Any other question in the chat? Maybe no questions in the chat. All right, so let's thank Nick again for the great talk.
Thank you very much.